This would be a mixture problem. So in this example, a chemist needs to prepare a specific concentration of sulfuric acid. It's sulfuric acid solution, actually. Find the amount of 14% sulfuric acid solution and the amount of 7% sulfuric acid solution she should mix to make 28 ounces of 13% acid solution. So what do I mean by those percentages? Yeah. So 14% sulfuric acid solution, the rest of it might be water or whatever base solution it is. And then if you could measure it out, 14% of the entire solution, 14 parts out of 100 parts, I like what you said, would actually be pure acid, right? Okay. So hard to draw a picture with this one, isn't it? Step one, though, we can name our unknowns to help us understand the problem. So look at the, well, I guess there's only 2 sentences. Look at the last sentence. Find the amount of 14% sulfuric acid and the amount of 7% sulfuric acid solution. That's our unknown, both of them, right? So how do we measure this? The units are there somewhere. Do you see it? How do we measure amounts in this case? There you go. You got to look a little bit, but it's in ounces, right? Very important in these mixture type problems to identify, it's important in every problem, but identify the units used and use them when you define your unknowns. On the test, this is going to be worth a couple of points, okay? So we're going to say let X be not just the amount of the first solution, but the ounces of the first solution, right? That's better than just saying the amount. Or you could say the amount in ounces if you want. So I'm going to say it like this. I'm going to say ounces, what's the abbreviation, OZ? Ounces of, the first solution was 14% solution. And you could abbreviate solution, SOL. Okay, so I like that. If you just say X equals 14%, I don't like that because that doesn't mean anything. Yeah, I know it does to you, but imagine somebody reading this who's not familiar with your work or not even that good at algebra. You want to be specific when you name your unknowns. So it may seem like being picky, but this is super important to help you understand the problem. Step one of Polya's 4 steps. Understand the problem. So based on that, then, what would Y equal? Ounces of 7% solution. You could use ditto marks if you wanted to, but it doesn't take that long to write it down, so I'm just going to write it down. Okay, it's a mixture problem. So you're adding stuff together. You're adding solutions together, right? So in mixture problems, I can't think of a time when you're not going to just add the unknowns together because you're mixing the things together, right? So you're going to have this equation you almost get for free. X plus Y equals something. Well, how much total solution do we want in the mixture? 28 ounces. So it's got to equal to 28. You're adding X ounces of the first solution, 14% solution, plus Y ounces of the 7% solution. So what X plus Y should equal, it should be measured in ounces, right? So X plus Y should equal 28. So this is just the equation involving amounts. And in any mixture problem, you're going to have that equation. You're going to add the unknowns together and get the amount of what it is you're looking for. Sometimes, I suppose the amount could be an unknown, but not in this class, because usually you're going to know how much solution you want altogether. So I don't show you those problems because they're kind of silly when you don't know the amount. So that's almost an equation you get for free once you identify your unknowns. But then you got to deal with the percentages. So, okay, let's deal with the 28. How much of the mixture, the 28 ounces, how much of that, percentage-wise, do we want to be pure acid? Yeah, so it says how much of the 14% and the 7% should she mix to make 28 ounces of 13% solution. We want this 28 ounces, we want 13% of that 28 ounces. There's the 13 right there. We want the 13% Of that 28 ounces, we want 13% of it to be pure acid. So can you put that in terms of an amount? How do you take 13% of 28? Go 0.13 times 28. Let's write that down, and I'll highlight what it means. So let's go 13%, 0.13 times 28. And that's going to be equal to something involving x and y, but we'll get that in a second. Let me highlight what this is. So this is 13% of 28 ounces, right? So that's the amount of the mix that's pure acid. Does that make sense? So it's the amount in ounces, right? Ounces of the mix that is pure acid. Very important for you to understand that statement to understand the problem. By the way, we're in step 2 now, where we're creating the equations, right? So the plan, we're developing the plan in step 2, and the plan is going to be to solve the system we come up with. But we're not even quite there yet. We're still understanding how to set up the second equation. But does that make sense, the 0.13 times 28? Now, what we need to do then is, we need to find out of X ounces of 14% solution, how much of that is pure acid, because we need to be adding pure acid plus pure acid to get pure acid. Does that make sense? So out of the X ounces of the 14% solution, how much of that is pure acid? It's the same type of operation, except it's 14% solution, right? So how do you take 14% of X? Yep. So you're going to take a little more room here, 0.14 times X. And let's highlight what that is. That's the ounces of pure acid that you need from the first solution or the 14% solution. But it's measured in ounces, right? We don't measure in percent. The amount is in ounces. Okay, do something similar with the Y. How much of the Y mixture is going to be pure acid? So this is 7%, so that's supposed to be a 7 right there, right? So 7% of Y, 0.07 times Y. So, 0.07 times Y, and we should be, this is the amount of pure acid from the second solution. We should be adding these together, right? Because we're adding these solutions together. So the ounces of pure acid from the first solution plus, remember what this is. This is ounces of pure acid from the second solution, the 7% solution, from 7% solution. So the pure acid, the amount of pure acid from the first solution in ounces plus the amount of pure acid from the second solution in ounces should be the total amount of pure acid in the mix. The units on both sides should match. If you understand that statement, then you can do mixture problems. Okay, so that's step 1 and step 2 of Polya's 4 steps. The first step, we identified the unknowns. The second step, we developed the plan. The plan is to solve these 2 equations, right? I guess we started the first equation up here. The third step is to actually solve these equations, isn't it? Okay, well, let's clean them up a little bit and then solve them. Let me back off this view a little bit so we have some room here. So going down here, let's rewrite. Well, the first equation we don't need to rewrite. X plus y equals 28, rather. And then we have, I'm going to write it as 0.14, so you can see the decimal point easier, plus 0.07, that's times x, plus 0.07 times y, what's 0.13 times 28? So multiply this out, 3.64. Okay? You could clear those decimals if you wanted to. What could you multiply through the second equation by to clear those decimals? Could multiply through by 100, both sides, right? Since I'm using a calculator, I don't really care if I do that or not. But if you want to, go for it. So I'm just going to leave it as is, though. What method do you want to use to solve that system? I think either one works just fine. Substitution or elimination. Let's use substitution. So what variable do you want to solve for? Y. So you want to solve for y. Okay. So in the top equation, I hope, right? Yeah. So what are you going to do to both sides to solve for y in the top equation? Subtract x, which gives me y equals what? So either negative x plus 28. If you want to write it as, if you think 28 minus x looks better, use that. I don't care. It doesn't matter, does it? Negative x plus 28 is fine. 28 minus x is fine here. The only time we insist on x being in front is when we put it in y equals mx plus b form, right? So, okay, what am I going to do with that 28 minus x? I'm going to substitute that in the equation I haven't touched yet, right? So that's y. It goes right there, doesn't it? Does that make sense to you? Okay, so then that gives me, what, 0.14x plus 0.07 times 28 minus x equals 3.64. Okay, what do we have to do here? Let's distribute. If you have your calculator handy, help me out. The 0.14x stays the same. Distribute the 0.07, 1.96 minus 0.07x, right? Equals 3.64. Everybody buy that? Okay. Combine like terms, you guys. So you have 0.14x and then a minus 0.07x. It's not, I think we can do that without our calculators. What do you get? 0.07x. 0.07x plus 1.96 equals 3.64. Subtract 1.96 from both sides. What do you get if you subtract 1.96? 1.68? Okay, I believe that. Does everybody see what I did? Subtract 1.96 from both sides. Everybody good? Okay, now divide both sides by 0.07. What's 1.68 divided by 0.07? You get 24 exactly? 24 what? Ounces. We'll summarize in a minute, but it doesn't hurt to put in the ounces right here. Okay, we also need y, don't we? So what's the easiest way to get y? Yeah, now which equation? I mean, it would be easy enough to plug it in this one, right? But there's an easier one. Does everybody see it? The one that you solved for y since we used substitution. So the idea is you could plug it right in there and then do it in your head in this case, right? 28 minus 24, 4. So let's see, we call the chemist a she. So she needs 24 ounces of which type? 14% solution. And 4 ounces of, what was the other, 7%? Okay, that's step 3, right? Carrying out the plan, executing the plan. The plan was to solve the system. And so we did step 3, I guess, starting up here of Polya's 4 steps. First step, understand the problem. Read, understand the problem. Second step, develop a plan, which means, so in the first step, we name our unknowns. In the second step, we set up equations involving those unknowns. The plan is to solve those equations. Third step, carry out the plan, solve the equations. What's the fourth step? Yeah, now you could check these in the equations, make sure it checks, and make sure you solve the equations right. But more than that, does it make common sense? Do these answers make common sense? Well, okay, look at what you're mixing. You're mixing a 14% solution with a 7% solution. And you want to get a 13% solution. So doesn't it make sense you'd use a lot more of the 14% solution when you mix these things together? And that's, of course, the case. So these answers seem realistic to me. Okay? So that's step 4. Look back, check your answer. So we did that.